Hi, so our final project on 460J was creating new movie posters through style transfer. So the process that we use was style transfer, which is a computer vision technique that basically takes two images, a content image and a style reference image, and blends them together so that the resulting output image retains the core elements of your original content image, but then appears to be painted in the style of the style reference image. And basically, the mechanism behind this process is a convolutional network, which determines the statistics of the content and reference images and then blends them using a feed-forward neural algorithm. So for this algorithm specifically, the way the style transfer is actually implemented is through a CNN. And in general, a CNN is useful because it uses individual layers that are trained for image classification to understand specific features of the image. The convolution layers put the content image through multiple convolutional filters, where some layers extract the content of the image based on like their position or shape, and other layers focus on style, for example, the frequency of brushstrokes. The feed-forward process, coupled with backpropagation, minimizes our overall error as explained by the distance functions L content and L style, because it first moves information from input to output in one direction and then works backwards from the output layer to update the weights of all the layers and reduce average error accordingly.
In terms of the general steps, we have 5 different steps. The first one being visualization, pre-processing, modeling, loss functions, and optimization. So we just had to broadcast the image array so that it had a batch dimension to normalize it for the display. For the pre-processing, we had to import the image and transform it into a torch tensor. And then for the modeling, we had to input that tensor into the model and then load the VGG19 model, which was used to extract feature maps. For the loss functions, there are 2 types, which we'll get into the next slide, the content loss functions and the style loss functions. And then on top of that, we decided to optimize our model using these loss functions. So there are 3 different loss functions that we use. The first one being the total loss function. We just needed to choose a set of convolutional layers where we wanted to place our content loss functions. And the content loss function is simply just comparing the feature maps of the content image with the input image after a particular convolutional layer in the network, and the output is just the mean square error of these feature maps. In similar regards to the content loss function, the style loss function is just comparing the correlations of the feature maps, which are the gram matrices, between the style image and the input image, and the output of this function is just the mean square error of these gram matrices.
So our content image dataset included over 1,000 old movie posters. These images would be the original images before adding the style to the content. We implemented 3 themes from famous art movements for our styles, including pop art, pointillism, and Art Nouveau. We included 5 images per style. Part of our pre-processing included resizing all of the data so that the content and style images were all the same size, allowing for a 1-to-1 dimension ratio. Here we show the output for our first official run using the VGG19 model. We were surprised and impressed by the outcome. You can see the girl and where the text are pretty well. We also attribute part of the lack of clarity to the lines between the face sections in the style image, adding to confusion. For example, we would expect to see a more clear style if only one of the faces was shown. The VGG19 model uses 16 convolutional layers, 3 fully connected layers, 5 max pool layers, and 1 soft max layer.
As we were narrowing down how to get the best results from our style transfer to really show a significant and noticeable change in style, we started tinkering with different parameters to get better results, which we will discuss more in the following section. So as mentioned before, we used the VGG19 model during our initial testing, and ultimately we found that this pre-trained model worked the best. This is a pre-trained, very deep convolutional networks model for large-scale image recognition. So since this is a model that has been previously trained on a large data set of images, it contains weights and biases that represent the features of the large aggregate of images it was originally created for. So these learned features are often transferable when working with different data. And we found this very effective to use with our data images, and specifically it yielded the best results when tinkering with the weights of the parameters. So in the next slide, we have the style weight and content weight were the two main parameters we started comparing. And as you can see on the left, the style weight, if it was set very low and the content weight weighted really high, you see a very small style loss and a moderate content loss. And the resulting image doesn't have much of a style transfer, although it retains a lot of the content. Then conversely, on the right, if you switch the weights and you have style weight weighted very highly at 1,000 and content weight at 1, you have a style loss and content loss that are both moderate, but at the output image, you can see you still retain quite a bit of content, but you get much greater emphasis on style transfer. So ultimately, we kind of concluded that the style weight needed to be much higher than the content weight in our models.
Cool. So yeah, now we'll get into the placement of our loss functions in relation to our convolutional layers. So the first thing that we did was we placed our style losses up to the very first 5 convolutional layers in the VG19 model. And we placed our 1 content loss under the 4th convolutional layer in our model. And we found out, based on the output image to the right, we can see that a lot of the colors from the style image are present in this new output image. And a lot of the content also really hasn't changed much. And that's because these earlier layers are focusing more on these simpler features, such as colors, simple lines, simple shapes. So they're not really going to affect the different objects and different texts as much. That's why we see like this nice integration of color in this new output image. Yeah, so the next thing that we tried was this placement after the 1st, the 3rd, the 5th, the 9th, and the 13th convolutional layer. And we placed our content loss after the 9th convolutional layer in the network. And we can see now that this output image is a lot more focused on these objects, like the text and like the other images, other objects at the bottom, and how they're styled in a different font in a different way. And this is because these higher level layers are focusing more on these objects and how they're tweaking them in a way like that. So that's why we're getting more of this emphasis on these text. Now we get into our models used. So yeah, I mean, the first model that we use is the VG19 model. We basically only use the 16 convolutional layers and the 5 max pool layers for our process. But yeah, these are basically the same parameters that we saw in the previous slides. And yeah, these earlier layers outputted a pretty well, really appealing output image movie poster. Yeah, so the next thing that we tried was a very, very small model. Only 3 convolutional layers, only 3 max pool layers, and very similar parameters for this one as well, but it wasn't really as good as refining the styles quick enough to really integrate it well into the output image. You can see that the styles are evident from the style image, but they're not really integrated well into the actual output image as a result. Now we'll move on to the AlexNet model, which is we only really use the 5 convolutional layers and the 3 max pool layers. Parameters same as the VG19 model. However, this one was a little bit different because with the VG19 model, the kernel size of these layers was like a 3x3. But for the kernel size of these layers, it was 11x11. So it would really focus on the higher level, the global scope of the features and not like the actual detailed style, detailed colors. So because of this, it's not really like being as precise as it should be. And it's kind of outputting this convolution of just colors everywhere, which makes like kind of a not really appealing output image. Yeah, so one of the next things that we tried was just multiple style images with just 1 content image. We tried the only thing that we had to add to this is just to add another style loss to our total loss function. As you can see on the right, we have a style loss, a loss for the second style function, and a content loss. And we're just basically doing the same process of style transfer. And you can see on the right-hand side that we have some different textures from the second style image plus some colors on the right, the pink and the purple from the other style image. So it ended up working out pretty well.
So our next approach was reverting style transfer just to see the lasting effects of a style transfer on an image. To do so, we generated a style image as shown before with the output image in the upper right. And the approach to reverse these steps was to utilize the original image as our new style image. And you can see that each of the iterations becomes clearer with 1 and 2, while the third completely loses the original image. Our first and second pass are almost completely identical, with the second pass only marginally better in color matching the original piece in comparison to the first pass. One pass seems sufficient in making the image recognizable in comparison to the original, while two passes make it truer to the original. The third pass leads to content loss inflation and completely lose the original image, save for some approximate matches for color locations. In the next section, we will be discussing our final approach and goals. In the next slide, we see that the main issue with our existing models is that text can sometimes get lost in the style transfer. So our goal was to generate multiple unique, interesting posters utilizing one source image while applying different styles in a way that still retains the text and identifying features of the original poster. Our three main methods in doing so were modifying the weights of the style and content image while also modifying the number of steps run. Additionally, we tried utilizing masks to transfer only portions of the image and merge the separated pieces back together such that the background is styled and the foreground is left alone. Lastly, we investigated the approach of segmented style transfer. And our first approach, we see that modifications produce a recognizable image with relatively readable text while still maintaining a lot of features of the style. This was our most successful method in producing recognizable text. It required a larger content weight, which produced a less styled image, but still maintained a lot of features of the original image. In our next approach, we attempted masking, which was relatively unsuccessful due to some issues with grab cut, which lead to issues with text identification and ultimately led to an unreadable foreground mask. This required different formats than our images that we utilize for our style transfer functions and ultimately led to unsatisfactory outputs with a lot of incompatibilities and patch fixes required. And the lack of transparencies led to masks for foreground that were unusable for merging. In our next slide, we can see some additional images with foreground and background detection and masking. And as you can see, it works a lot better for objects, but not so much for text. And in the next slide, you see the results of style transfer on the foreground and background. In our third and final approach, we looked at segmented style transfer. However, it had similar issues to method 2 and produced no usable results with similar issues to masking due to private libraries, difficult alter functions, and a lot of issues with matching our input and output formats. In the ideal situation, this would help us to utilize an identifier to denote sections that we wish to style, marking objects, person, text, scenery, etc., to isolate pieces of the background to stylize each piece, while avoiding the text completely to produce a recognizable output. However, this did not work. In the next slide, we will go over our conclusion.
So in conclusion, through our results, we found that out of all the models we used, the VGG19 model worked the best. We had better results when style weight was weighed higher than content weight. And for the purposes of poster stylization, model modifications worked best, but masking and segmented style transfer did not. The algorithms used struggled to find the areas to mask and properly apply those to the style. Thank you.